Okay, so now we're going to talk about some basic hill slope geomorphology, because it's important to understand how hill slopes come about if you're going to design the slopes of a rehabilitation, or design the rehabilitation of a rock dump, for example. How do you build a hill slope? Well, let's go to nature and look for some answers, and I'm going to be showing you along the way some slides that have been provided by Greg Hancock from Newcastle University. So, there are current designs which dominate in reconstructed hill slopes at mine sites, and that's a berm and bench approach, right? So you have a linear slope with a bench which is often angled backwards to stop flow accumulating downslope, and then another slope. And then if you've got really long hills, you may have 2, 3 or 4 of these berm and benches. But natural hill slopes don't look like this, right? A natural hill slope profile is typically composed of 2 parts. A convex part near the top of the hill and a concave part which is the bottom part of the hill, right? So why are reconstructed hill slopes not built like natural hill slopes? Well, people are actually starting to now build the hill slopes with convex concave slopes. Design. They're a little bit more challenging to design because you need to challenge the pre-existing paradigm, right, of how these slopes are built. So you need to train people on how to build them, and you need to design them properly for a particular climate and a particular soil. So what are the advantages of concave slopes? Well, firstly, you have a rapid drop in elevation at the higher parts of the hill where it's steeper, but you also have little runoff, right? You've got a high slope. But at the same time, there are also places where you have small amounts of runoff. So even though the slope's steeper, the flow velocities are going to be low because the total amount of runoff is going to be low. The lower slope at the bottom of the hill is where there's maximum runoff, and because you have less slope, your flow velocities should be lower. And it turns out that this concave profile actually reduces the total energy of water flowing over the hill slope, right, where it has the greatest force. So how do you design a concave hill? Well, all hill slopes conform to this slope area relationship, and typically you have the area above a point that's contributing flow is proportional to some constant times the slope raised to some power, right? And this area slope relationship, right, defines the contributing area, and if you have a big rainfall event, that contributing area is going to be somehow related to the total amount of flow flowing through that point. And you can actually look at the natural landscapes to look at their area slope relationships if you want to design a landscape that looks like the surrounding landscape, right? So measure the surrounding landscape, look at its area slope relationships, and then maybe design your mining landscape to have a similar one, or design one that you think will look good or do the job for you. So typical slope area relationships look like this: a logarithm of the local slope versus the drainage area flowing through that point. And typically you have this sort of shape. You have an increase in the slope gradually on hill slopes, and then where you have channels starting to develop, then we have a decrease in the slope as the drainage area continues to increase. Right? It's not quite as simple as that, and we'll show you examples of what's going on. So let's go to some real data. This is a drainage area from somewhere called the Yellow River. We're looking down at a catchment, and water's flowing through this catchment from the top here, down through this blue line here and out this end of the catchment, okay? And maybe I've got that in the wrong way. No, it should be the right way around. Everything's going through here. So this area defines the catchment boundary, and the upstream contributing area is actually this whole area. If we had a really massive rainfall event, all the water from all parts of this landscape contribute flow through this point. And within that area we have little sub-catchments or tributaries. So let's focus on this little catchment here. So the upslope contributing area for this tributary at this point is this catchment. Okay, and that's only one component of this larger catchment. And if we develop a slope area relationship for typical catchments like this, we get a pattern that looks like this. These are actual data points from a digital elevation model. This is like a rasterized grid of the topography that's been put into a computer, and you can calculate these numbers. And you can have a look at the local slope versus the cumulative drainage area. And so we have this increase here in region 1. And this increase here is predominantly dominated by convex slopes. Okay, we have diffusive sediment transport processes occurring here. Things like rain splash, soil creep, we have bioturbation and all sorts of things that are contributing to this increase in slope. And that's the convex part of the slope. Then in region 2, it starts to plateau and begin to decrease, and this is where we get gullies forming. Natural, in natural systems we still have gullies forming, or we get nick points where the ephemeral flow channels are occurring. Then in region 3 we have Hillslope fluvial section. We're starting to begin, we're beginning to get proper permanent channels. That maybe not always flowing with water, but that you've got a well-defined hydraulic geometry. And then in region 4 we have a well-defined channel in parts of the landscape. Yeah. And the slope begins to decrease then. We can look at areas from all parts of the world and catchments, and they all follow the same sort of pattern. This is from Utah, using a digital elevation model, and again we get this increase, this plateau, and then maybe a second section here and then a gradual decrease further along. This is an example from the Pilbara where we've got mesas here, so we don't really have that convex part of the slope, right? We've got this flat plateau. We've got very little, no convexity to the hill, or almost none. That's difficult to measure using the elevation model that we had. And then we get this decrease, this concave slope coming off the mesa. Right. So in the case of the Pilbara, the slope of that line was equal to 0.41, right? And this K star here this depends upon how long your slope is going to be. So you can actually replace this area by distance if you want to. If you have a planar slope, you don't have converging flow. So the distance is proportional to K times the slope raised to this power. So you can, using this equation, you can construct the height of the hill as a function of slope length, right? By varying this K parameter. So let's say we held alpha constant. Let's assume that it's 0.41. And so we can essentially have the same exponent but have different hill slope lengths if we started from some constant height, for example. And they give us different average slopes, right? From the top to the bottom we get an average slope. In this case 13% when we have the longest slope and 45% when we have the shortest. Okay. Now on the other hand, if we have a variable alpha but a constant slope length, you can see here we have the same height and we have the same slope length in each case, and we gradually increase alpha from 0.2, it's almost planar, and then we gradually increase it up to 0.5, we get increasing convexity, concave slopes, increasing concavity in the slope. So what happens to the sediment loss depending upon this alpha parameter and the slope length, right? How does the concavity impact the sediment transport? Well, Greg set up a model using his model Siberia that modeled the sediment loss over 100 years, and he looked at the average slope using a constant alpha, and he did the simulations and estimated the sediment transport. So with an average slope of 20%, the slope length was 200 meters, The sediment loss was 22.3 tonnes per hectare per year, and the sediment loss, the sediment loss from a linear slope of the same length, right? So linear slope, and instead the sediment loss from a concave slope, the same length but with a concave section, we had 0.4 of a tonne per hectare per year. You can see in each of these cases, comparing the linear slope with the concave slope, we had much less sediment transport from the concavity. And that's because of this change in slope with distance. We get a decrease in slope towards the bottom of the hill. And this leads to a decrease in the flow velocities and a resultant decrease in the sediment transport rates. On the other hand, with a variable alpha, constant slope length, right, we had alpha is equal to 0.2, the sediment loss, these are all concave slopes. We can see that as the concavity increased from 0.2 up to 0.5, our sediment transport rates all decreased. Right, so even though, in this case here, we have the steepest slopes of all these cases, the steepest slopes at the top of the hill, we get the lowest total sediment transport rates after 100 years. So concave slopes are good compared to linear slopes. So why would you build berm and bench slopes? Well, often the engineers argue in favour of them. Okay, so the advantages of concave slopes: sediment loss is greatly reduced. You have the potential for greater long-term stability, and they also look more natural, right? They blend in better with the surrounds if you have hills in the surrounds. The disadvantages of concave slopes: they can be difficult to construct, right? Especially at the top of the slope where you have very steep slopes, and you may, it's very difficult to engineer or to bulldoze them into the slope, particularly if you've got angles now approaching 30 degrees, which are at the limit of where some of these machines can operate. With concave slopes, the footprints of the hills are often greater than that required by conventional designs. Not always, but they can be. So better planning is required to design them. And even if you have concave slopes, you still might get gullies and erosion happening because of the materials that you have on them. Okay. So typically it's a compromise between a berm and bench type design, okay, or a concave design which has a larger footprint. And mining companies are worried about this footprint because they often have to pay bonds depending upon the size of their mining footprint or where they impact the land.